Hello, my name is Aisun. I'm a student at Seattle U of Distributed System class. This is Mo, my assistant. Today we're going to talk about implement remote procedure call.
This paper was presented by Andrew D. Burrell and Bruce J. Nelson, two brilliant computer scientists at 1984. When was that time? That was the time the distributed systems were still at the early ages. If you want to let programs talk with each other, they use low-level network communication interfaces like sockets to exchange data. Programmers would write huge amount of code to achieve the goal. The complexity was a disaster. Also, the code was difficult to maintain. The network communication needed to become easier for distributed systems. That was the time the implementation of RPC came out. It provided one of the solutions to simplify distributed computing and making remote procedure calls as easy as local calls. Let's dive into it right now.
Programmers are very familiar with local procedure calls. If you make remote procedure call behave exactly like a local call, it will be much easier to accept and use without any obstacles. That's also the main purpose of this paper, which is simplify remote procedure calls to achieve an experience similar to local calls without considering communication issues. The secondary purposes are efficiency, security, also provide complete end-to-end communication. The outline of the paper includes introduction and structure of remote procedure call, bonding, packet level transport protocol, performance, and further discussion. In the paper, the authors focused on 4 problems with this amazing approach, providing solutions for each one of them. First problem was how to handle server failures or communication failures. Well, the RPC package ensures that if a procedure is invoked and completes, it is done exactly once. If a server or communication failure occurs, the user is notified through an exception, without knowing whether the procedure has been executed. If a server crashed and restarts, the call is retried, and unique identifiers ensure that all data isn't reused. Additionally, binding is broken implicitly if server crashed, informing the user of any failure between calls. How to integrate remote calls into existing system. The RPC system integrates into existing programs by using stubs, automatically generate codes that handles transfer of arguments and results between machines. This will allow users to write normal local procedure calls in your code, while RPC system handles communication with remote servers. The RPC package using the Grapevine distributed database for binding, which connects the client to the appropriate server. How to transmit data. The RPC system uses a custom transport level protocol designed only for RPC, optimized for minimum transmission delays. Simple calls transmit in 2 packets, one for the request and one for the result, with auto acknowledgement. For the larger data, packets are sent sequentially with acknowledgements for each. The protocol ensures the integrity of data transmission using sequence number and call identifiers. How to ensure the integrity and security of data? The RPC package provides encryption-based security. It uses the data encryption standard, also goes by DES, for end-to-end encryption of calls and results. Grapevine is used for authentication, ensuring that both caller and callee identifiers are verified before communication. In this paper, packet level transport protocol is a huge part of content, for it is exclusive for the RPC implementation. So we're going to talk more about it. The goal of this design is to reduce the delay, which means latency, when making calls over the network. There are 2 options discussed in the paper. The first option is use the existing Grapevine protocol. Well, the author said its performance is not great. The second option was set up a special communication channel for making remote procedure call. It goes with the advantage that this method performs much better, over 10 times faster than using the grapevine protocol. If you're sending a lot of data and it takes a long time, it's okay to create and close connections as needed. The time spent setting up and closing the connection is much smaller than the time needed to send all the data. If there are many RPC clients constantly creating and destroying connections, then it's better to use long-lived connections to avoid extra work. If something goes wrong during the call, the server should stop right away and send back error information to the caller. This error could be due to network issue or the server crashing, though the user might not know which one it is. If the server goes into an infinite loop, let's say stuck in endless processing, it won't return an error, just like if the same thing happened locally. During a call, the caller sends a call ID, the parameters for the call, and the information about the message to be called on the server. The server decodes the message, runs the requested message, and sends back the result. The sender, which could be either the client requesting the server or the server sending the result, will assign a sequence number to each data packet and wait for an acknowledgement for the other side. Both the server and client can be sender depending on who is sending the data at the moment. Call IDs are used for two purposes. The first one is to distinguish between different requests for the caller. Second is filter out duplicated requests for the server. The call ID is combined with machine identifier, process identifier, and sequence number. The sequence number always moves in one direction, such as increasing. It doesn't need to be continuous though. Since the call is tied for specific progress, the RPC system on server machine keeps track of the last sequence number it saw for each call. When the server gets a new request, it checks if sequence number is higher than the last one it saw. If it is smaller, the request is discarded since it's a duplicated request. The sender of the data packet is responsible for retransmitting any data that has not been acknowledged by the receiver. If the call takes a long time, the caller will periodically send 4 packets, which the callee will acknowledge. The benefit of this is that in case of server crash or communication failure, the caller is notified. The frequency of these 4 packets decreasing over time until it reaches 1/4 every 5 minutes. If the 4 packet never receive a response, the caller will assume there's a communication problem and take appropriate action. If the data packet sent by the sender is too large, it will be split into multiple packets. All packets except the last one must be acknowledged by the callee. Both the caller and callee only use the 1 packet buffer. To eliminate duplicate packets, each sent packet has a corresponding sequence number, as the image below. A call initiated by the user is split into 2 packets due to the size of the data. Assume the split packets are packet A and packet B. When sending packet A, the server receives it and sends an acknowledgement to the user. Then packet B is sent. Also, the server receives packet B, it does not send an acknowledgement for packet B to the user for some reason. Since the server has received both packets, it combines them, A and B, restores the original data, and proceeds to execute the call. Meanwhile, the user suspects that the server may not have received packet B, so it retransmits packet B. When the server receives a duplicated packet B, it checks internally and finds that it actually had received its packet earlier. The server then immediately sends an acknowledgement for packet B to the user. How important is the implementation of remote procedure call? The paper was cited by a huge number, and it laid the foundation of lots of further researches, implementations, and applications. In my opinion, RPC will continue to play an important role for it is significant for distributed systems.